going to talk about more conservation of energy, and specifically, Matt, we're going to ask, what if the potential energy isn't MGH? You're not lifting something. And a great example is example one. I like example one. I'll tell you right now, on your test, there's either going to be a slingshot or a bow and arrow question, because to me they're the same physics. I have great memories of slingshots. When I was growing up, we had a cabin out near 100 Mile House, and we would go there in the summertime. And the first full day, we would get there in the afternoon, we would unpack, go to sleep. And then first thing in the morning, my dad, my two brothers, and myself, the four of us would go hiking into the woods, and my dad would carve us all slingshots. And we had them for the rest of the trip. And we had a beach with millions of rocks, and so we spent hours and hours and hours firing rocks out over the lake into the water, or trying to make them skip, or bouncing them off trees. It was hours of fun. So I love slingshots. That's a hint. Also, I used to teach archery when I was a summer camp counselor, so I'm telling you, it's either going to be archery or slingshots on your test. They're dear to my heart. A slingshot is pulled with an average force of 70 newtons for a distance of 97. Nice try, Duick. How many meters? 0.9. Matt, what's A want me to find? Don't write this down, look up. This is one that kind of bugs me. I see kids do this. Oh, potential energy, that must be MGH. And then they start to panic. Don't write this down. They go, I need there's a mass in part B. There's the mass. So there must be an H. Well, H is in meters. So that's meters. That must be a height. Is this a height? Heights are in what direction? The vertical direction. And I'm going to say this to me is a silly, panicked guess. What does it want me to find? But not gravitational potential energy. So how the heck can I find it? Energy is the ability to do work. So everything comes from what's work. Oh, no, you're right. Yes, the potential energy here is going to be force times distance, not MGH. What's the force? Yep. What's the distance? 0.9. Pretty sure that's 63 joules. Double check me, but I think 7 times 9 is 63. Matt, let's keep going. If there is a 35 gram... Nice try. 35 grams. How many kilograms? Divide by 1,000. If there's a 35 gram, 0.035 kilogram mass in the pouch, how fast will it leave the slingshot? Matt, what's this question asking me to find? Now, you might think that if it was asking us to find velocity, I would go back and I would look for, well, is there a VI? I guess you could argue VI is 0. Is there a D? I guess, but I don't know if there's an A or a T. I think it's asking me to find a speed. I think I would use conservation of energy. But I'm not going to walk through the full formula. What energy transformation is going on in either a slingshot or a bow and arrow? What's turning into what? You might recall the video I showed you of the girl in the human slingshot. I would just skip the whole initial plus initial equals final plus final, and I would just say, you know what? All of my potential is turning into kinetic. Because, Matt, I know how much potential energy I have. How many joules of potential energy are stored in this slingshot? Good. I'm going to get this. 63 equals a half mv squared. And there's the v that you were talking about that they were asking us to find. Now we just got to get it by itself. How would I move the m over, folks? How do I know? What's the m doing to the v? Multiplying, so we would divide it over. What about this 1? Who cares? What about this 2? Well, it's on the bottom, so I would times it over. Now, the other thing you can do is just divide by 0.5, but I don't like having a decimal inside of a fraction. I think, Matt, I would get this. 2 times 63 divided by m, that equals v squared. Matt, v what? So? Yes. Good. The speed is going to be the square root of 2 times 63 divided by 0.035. This might work out evenly. It has a chance, at least. The 7s are canceling, so you might get a perfect square. Did you?
Oh, yeah, I did the wrong stuff.
60? Units? Is that a reasonable answer from a slingshot? I know a football field, like our field back here, is roughly 100 meters long, so this would be a little more than half the field in 1 second. That seems about right. That's faster than a person can throw, but nowhere near as fast as a bullet. That would be moving fast, but I could also kind of see it coming with my eyes. Yeah, that seems right for a slingshot. Sure. Ballpark figure anyways, that seems okay. So one nice application of the law of conservation of energy is slingshots and bows and arrows. Is that all right? What else? Rope swings. I didn't grow up in Pitt Meadows. Is there a good rope swing over a lake anywhere? Has someone put one in on Pitt Lake or anything like that everyone knows about? Is there a good cliff jumping location that everyone knows about? I've seen a few people jumping off the Silver Bridge. I think that's technically illegal, so I can't recommend that. Okay. I was a camp counselor out in Hope, and on the lake there, someone had put in a really nice rope swing over a nice deep area, so you don't have to worry about hitting the ground, and it was a well-made one. So, too bad. Rope swings are great examples of conservation of energy. Tarzan weighs 82 kilograms, should say has a mass, because weight is technically mg, but that's okay, and can run at 8 meters per second. He runs along the ground and grabs a vine, swinging into the air. So I guess taking a run along the ground and just grabbing a rope, how high can you swing? What does DOLP stand for? Draw a little picture. We're going to draw a little picture. So here's Mr. Duick's picture. Here's Tarzan running really fast. That's about as good as I'll ever draw anything. Here's the rope swing. So I guess Tarzan is going to grab it and start to swing up into the air. Does that make sense? That's what I'm visualizing here. Ella, here's really what I'm noticing. After Tarzan grabs the rope, will there be a change in height? Will there be a change in speed? Will there be a yucky, curvy path? What would my best approach for solving this be then? Conservation of energy. Okay. K-E initial plus P-E initial equals K-E final plus P-E final. Plus heat, does this question say to include friction? Then are any of these zero? Let's look at kinetic energy. Is he starting out at rest?
No.
Is he ending at rest? Someone said yes, someone said no. The good news is one of those people is right. At the top of the swing, Ella, how fast will you be traveling for it? I think I can say, yoink. What about potential energy? Is this on the ground? Is this on the ground? Here's the beautiful thing about conservation of energy. Because it's a scalar, it doesn't care what you decide to use as your frame of reference. Let's put the ground there. It'll give us the right answer. So, yeah, because, oh, that's too long. Yeah, because we can put zero high wherever we want to. If you really wanted to, you could put zero high at the top of the roller coaster. You'd have to adjust all the rest of your heights accordingly. Some of them would be negative, but the physics would still work. You'd still get the correct answer. And so sometimes it's easier to put zero at a weird location to make your life easy. And this way, I don't need to know how tall Tarzan is. In fact, I think I get this, a half mv initial squared equals mgh final. Matt's going to put his phone away because he's just not that important. Ella, is there an m in the first term? Is there an m in the last term? Is there an m in everything? So what happens to the m's? What does that mean in real life? Well, it means not only will Tarzan swing to this height, but if Tantor the elephant was running at 8 meters per second, and if the vine didn't break, an elephant would swing to the same height as Tarzan. The mass is irrelevant. The key is you better be doing 8 meters per second. Oh, and in Tantor's case, you better make sure the vine doesn't snap. What are we trying to find? I would also have no problem giving you the height and saying find the speed. But how would I get the height by itself? I'm fine with that. Ella, I would, because I don't like decimals as much, I would have written it as VI squared over 2g, and I would have been so lazy I wouldn't have bothered putting the 1 from the 1/2, but dividing by 2, timesing by 0.5, same diff, I don't care. So it's going to be 8 squared divided by 2 times 9.8, or 0.5 times 8 squared divided by 9.8. It's going to be 64 divided by roughly 20, 3 point something, but I can't get much more than that. 3.27 meters. So, rope swings. Yay. What else? Oh, water slides. Also a good example of conservation of energy. Although in real life, you lose a lot of energy because your body is actually pushing the water around as well. And so the water bleeds a lot of energy from you. Technically, at the bottom of a water slide, you should exit it at the same speed that you would hit the ground at if you jumped off the top of the water slide. You don't, and they've made very sure of that. Although some of those speed slides, it's pretty close. Those are way more efficient. But most of the curvy ones, you're losing a lot of energy around those corners on purpose for safety. Slap shots are great examples of energy transformations. Any hockey players here? No one in this class. Okay. We'll watch this video, but we'll watch it later. We'll come back to it. Instead, let's go ride a roller coaster. The roller coaster has a mass of 255 kilograms. If the coaster just barely makes it over the first hill at location A, so let's assume VI is 0, how fast will it be going at location B? Okay, I'm going to call this initial. I'm going to call that final. Tyler, if you look at this picture, is there a change in height? Is there a change in speed? Is there a yucky, curvy path? Any suggestions on how I might want to solve that? Yes. I even thought I heard an echo. Conservation of energy. Yeah. So, Tyler, it's going to be KE initial plus PE initial equals KE final plus PE final. Which ones of these are 0? Let's do potential energies first. Those are going to be 0 when we're on the ground. Are we on the ground initial or are we on the ground final? Zeros are always nice. Kinetic energy will be when we're at rest. Are we ever at rest? So again, something that looks really complicated, not too bad. I'm going to get mgh initial equals a half mv final squared. Tyler, you like roller coasters? What's your favorite? Okay, man. Pause for a second. Okay. Tyler, clearly you've been on some coasters before. Before you went on the coaster, did they make you step on a scale? Do they have to spread out big kids and little kids? Can little kids and grown-ups go on this ride? Why? Because what happens to the M's here? They cancel. If we include friction, they don't, but if we grease it down, they nearly do. We're trying to find, I guess, V. Okay. Again, you can divide by 0.5 square root. Tyler, I like to times the 2 over, like this. And then divide the 1. Although, will I bother writing divide the 1, Gibson? And I get VF squared equals that. So it's going to be, square root. It's going to be the square root of 2 times 9.8 times 18. Tyler, let me know what you get. I think this is going to be okay fast, but not crazy fast. This is almost 20 times 20, so it's almost the square root of 400. I'm going to guess you're going to get something in the 18s or 19s. 18.8? Round it off properly? Could you times that by 3.6 again in our obligatory, hey, how fast is that? Okay, that's more than a meh, but that's not a, that was life-changing. I'd stand in line for half an hour, 45 minutes for this ride. But I stood in line for 2 hours for X2. I'm not standing in line for 2 hours for this. B. All right. So, same question, but what's not 0? KE initial. So Josh, let's start out the same way. It's still going to be conservation of energy. G. KE initial plus PE initial equals KE final plus PE final. But this time, Josh, that's the only 0. Okay. Oh, also, pretty sure we'll be going faster than 18.8 at the bottom. How much faster? So let's bring in our half m v initial squared plus m g h initial equals a half m v final squared. Josh, do you like roller coasters? What's your favorite? Wow. Wow, wow. Okay. Have you been on a roller coaster before? Before you got on, did they make you step on a scale? Why not? Okay. Mr. Dewick, are there some rides where mass doesn't cancel? Bumper cars. Those would not cancel in the collisions. That might be it. Further research is necessary. I'll have to go to Playland this summer and double check for myself. Those are research projects that are kind of fun. Josh, what are we trying to get by itself? The VF? There's 2 ways to do that. I have no problem if you go divide by 0.5 and square root. I like to clear fractions. I like to go times by 2, times by 2, times by 2. The only reason I like to do that is it brings a familiar friend. VI squared plus 2GH initial equals VF squared. It brings back VF squared equals VI squared plus 2AD. I like that because when it shows up, I know I've probably done this right. But it's actually one of the few times I'm writing an extra line of work because dividing by 0.5 square root, you would get there in 1 step. I'm actually having to write 1 more line. So, okay. It's going to be the square root of 22 squared plus 2 times 9.8 times 18. 28.9? Could you do the obligatory times by 3.6? Okay, this one I'm willing to stand in line for. I've been on faster, but I've also been on slower. So yeah, I'll give you maybe 90 minutes of my life to go on this one. Depends who I'm with and what the weather is. If it's raining, no. So let's suppose we went on the ride in part B, but instead of traveling 28.9 meters per second, we got a radar gun out and we're traveling 25 meters per second. How much energy was lost to heat? Okay. Noor, how am I going to handle this? Is there a change in height? Is there a change in speed? Is your yucky curvy path? I'm still going to do conservation of energy. Oh, except this time, what do they want me to include? Okay. KE initial plus PE initial equals KE final plus PE final plus, and I'll do my usual heat in fiery red so it stands out. Which of these are zero, Noor? Sadly, again, I think only one. We're ending up on the ground, but we're not starting at rest this time. Noor, how would I get the heat by itself? So the left side's going to drop down like a domino. That equals heat. Oh, you've been doing heat in red, Mr. Dewitt. Be consistent. All right. Heat is going to be a half m initial squared plus mgh initial minus a half mv final squared. Do the m's cancel here? Isn't there an m in everything? What isn't there an m in? Oh, heat doesn't have an m in it. Okay. You know what? Let's be bold. On a test, I would absolutely show the numbers. Let's see in our notes if we can go straight to our calculator from here. What was the mass? 245? 55. 255? So it's going to be 0.5 times 255 times, what was it, 22 squared? Plus 255 times 9.8 times 18, I think was the height, minus 0.5 times 255 times, what did they say, 25 squared. I got almost bang on 27,000. Is that right? Anybody else? Yeah, got one nod. Two nods? Okay. To 3 sig figs, I guess it would be 27,000 joules. By the way, this is wasted energy. This is similar to the wasted energy in your car when you step on the brakes. When you step on the brakes, does your car speed up or slow down? Does it gain kinetic energy or lose kinetic energy? Lose. That energy's got to go somewhere. Not potential. There's no way to store it, like the gasoline engine. It goes into heat. Your brakes heat up. It's wasted energy. Where does it go if you have an electric vehicle? We know? Yeah, this is what they mean by regenerative batteries. It goes, or regenerative braking. There, they bleed off the energy back into recharging the battery. It's a very clever system using something called a back voltage or a back EMF. If you're bored sometime, I can walk you through it. But this is also one of the reasons that electric vehicles or hybrids are so much more efficient when you're stopping and going a lot. What do all the taxi cab drivers drive now? Priuses. Why? They ran the numbers very quickly. They were one of the first people to adopt Priuses overall, because the more you're hitting the brakes, unlike a gas engine, which makes your gas mileage worse, makes your gas mileage, your electric mileage, whatever you want to call it, better, because you're getting, not all, but a big chunk of the energy back. Most of you don't have your license. Has anybody driven an electric vehicle? Okay. I took a Tesla for a test drive a few years ago, and the first thing I noticed, in a gas engine, when you take your foot off the gas, you coast. In an electric vehicle, when you take your foot off, first of all, they won't let you call it a gas pedal, because there's no gas. They make you call it a go pedal. Okay? So when you take your foot off the go pedal, it feels like you're hitting the brakes, even though you're not, because it's bleeding the energy off back to the battery. It's bleeding kinetic energy. And if it's bleeding kinetic energy, what has to happen to your speed? You have to slow down. So it's really weird. I remember saying to the salesperson, like, I'm slowing down to come to a stop, but I'm not hitting the brakes to do it until the very, very end to make myself stop that final little bit. But I'm hardly using the brakes. The salesperson said to me, yeah, we tell people get your brakes checked every 10 years or so. Where for a gas vehicle, you get your brakes checked every year. Example 4. A car and rider start from rest. You know what? I would probably underline the word from rest on a ramp. At the bottom, the car is traveling at 15 meters per second. How much energy was lost to heat? Okay. Huh. Gerard, any suggestions on how I might want to solve this? First of all, what are they asking me to find? Heat energy. That's already a hint. Is there a change in height? Is there a change in speed? Is there a yucky curvy path? No. Have they mentioned heat? This is a job for conservation of energy. So we've added another condition to our little mental checklist. KE initial plus PE initial equals KE final plus PE final plus heat. Which ones of these, if any, are zeros? Gerard, my friend. Oh, it says from rest? Nice. What else? We end up on the ground? Okay. Anything else? Okay. How would I get the heat by itself? So you're telling me that heat is going to be potential energy final minus kinetic energy final? Sorry, potential energy initial. I agree. You know what? Let's see if we can go straight to our calculator from this line. Again, I would never, on the test, make sure you show me your equation, Natcha, and what numbers, but in our homework, let's see if we can go to our calculator. It's going to be mgh initial minus a half mv final squared. Again, I'm going to guess it's probably something in the thousands or tens of thousands, because that's usually where it is. Gerard, what'd you get? What'd you get? Okay. What'd you get? I think you get 6262.5. I didn't do that one in my head. I just remember that pattern from this morning. Right, 6262.5? Yeah. And I'm going to write down all the sig figs just because there's a part B, and often Mr. Dewick requires me to use my answer from A to do B. Mara, what's B want me to find? My first thought would be friction is what times what? Mu times the Why doesn't that work? And we don't have a normal force either. Okay. Any suggestions? Hey, maybe I can use my answer from A. How would that help me, Mara? I know you've been away. Any suggestions? Remember, another word for heat, it's also the work done by friction. How much energy friction bled off. So yeah, maybe I could write this heat as force of friction times distance. Ah, okay. How would I get friction by itself, Mara, my angel? So it's going to be the force of friction divided by the distance. It's going to be 62.5. Which distance? The 18? Sorry, is it the 20 or the 60? Why? Because for the work equation, the force and the distance have to be in the same what? Direction. So 20 is not in the same direction. Friction would be in this direction. I'll use the 60. You could argue it's negative because you're losing and it's in the opposite direction. I don't care. I'm just going to divide by 60. How big is the average force of friction? 104 newtons and change. Okay. Those of you that sign up for Physics 12, you'll find in the forces unit, we do a lot of stuff on ramps at an angle. So this gives you a little taste of some of the stuff we might look at. I talked about Rube Goldberg machines. Yes, I love chain reaction or Rube Goldberg machines. Put your pencil down. Here's a really good one. Spot the energy transformations. It's called the blue marble, so the blue marble has to make it through. Lots of different ways to store potential energy. Most of them are gravitational, but not all of them. Little cleverness with magnets and momentum there. Oh, nice. You can imagine how much could go wrong in the setup and the trial and error. So those types of things, they take hours and hours and hours. Another really neat application. How many of you have ever played with dominoes where you stack them in a row and then push the first one and have them all fall? Have you done that? The Netherlands has a really neat tradition. They have an event that's called Domino's Day, where they actually rent one of their soccer stadiums, an indoor stadium, and every high school in the country is assigned an area. They send their domino team to that area, and they have to build part of a domino chain. And then in prime time that night, the whole TV, everyone's watching it on TV at home, they show the whole thing, which is kind of cool. That's a neat tradition. A bouncing ball is a great example of the law of conservation of energy. So, first of all, at the top of its bounce, what type of energy does the ball have? Can you all write underneath part A, PE, or you can write potential energy? What about at the bottom of its bounce? Okay, KE. If I just drop this, it loses height on each bounce. Does that violate the law of conservation of energy? Okay, so PE, KE, no, we lose energy to sound and heat. All right, smarty peoples. If I drop this, is it possible for the ball to bounce higher than if I drop it? So can all of you write no for part D, and then I'll show you Mr. Duick's clever cheat. So, no, unless I cleverly stack a ball on top of another ball. You can do three.
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm going to try the golf ball on top of the bouncy ball, on top of the basketball. And then I'm going to explain how it's related to a supernova.
I don't know if you saw
that? Probably
that
not. So here it is again. The golf ball bounced.
That's spectacular.
To 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Let's simplify it to these two balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop. As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you combine them, the tennis ball goes higher than its dropped height. Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when three balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from two more massive objects into a smaller object, and it will go much faster. Epic! Just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum into the smaller balls, energy from the dense core of a supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity.
Nearly the speed of light.
More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of stars exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
I love Physics Girl. Her name is Diane Cowan. She's one of my nerd heroes, although she's dealing with long COVID, been hammered by it. I'm one of her Patreons, and so she's been out of commission for about 6 months and counting. But this is one of the few videos where she disappointed me. Did you hear her say we couldn't get 4 balls in a row to work? I'm disappointed. She didn't try hard enough. A golfer wants to hit their drives further by increasing the kinetic energy of the golf club when they strike the ball. What would have a greater effect on the energy transferred to the ball by the driver? Doubling the mass of the club head or doubling the speed of the club head? And convince me. Over.
The speed is squared.
What's squared?
It's the speed is squared.
Oh. So because KE equals a half mv squared, you're saying if we double the speed, how much more energy will we have? Yeah, 4 times the energy. And in a perfect world, you would get 4 times the distance. It's not quite like that because there's always some energy loss along the way, but yeah. Absolutely. What's your homework? Again, it's a long weekend. I'll give you some time to work on this on Tuesday. This is going to be due Wednesday, but here is what I assigned my Block Cs. Sadly, most of them, I'm just going to tell you which questions you can skip. You can skip. I think the only one I skipped was number 9. I think I said 9. So you can cross out number 9, but you can try the rest. And then I don't know if you recall, I did promise to show you a video about slap shots, so we'll look at how those work as well. You can work on the homework, or you can watch the video I'm about to show you. I just don't want to see headphones or people staring at screens. I'll go a little cray-cray. I said 9. Noor, I see your hand up. Hang on one thing at a time. Let me first of all hit pause.